Welcome to Paleopedology. 435, 535, most of you are 435. Um, Paleopedology. It's an odd topic, uh, and this is the last time I'll teach it because I'm retiring in June after 40 years here at the University of Oregon. And I feel like the University of Oregon has been really pretty remarkable in sponsoring a course in fossil soils for all those years. It's a field that has grown tremendously, but still only taught in a half dozen universities around the world. I hope you'll find it's a very interesting topic, which is actually quite important for understanding global change. Well, let's get to mechanics first. I'm Greg Retallack, of course, and this is the first lecture. I'll try to post the lectures before the time of 11 a.m. on Mondays and Wednesdays. The whole syllabus is, I think I emailed you one, but it's in this course packet, which you'll definitely need to obtain. There is going to be a lab in person, so I'll get to know you all, which will be just great. It'll just be just me, and it'll be in Columbia, room 47. But the lectures will be posted here for you to listen to at your leisure. It is a good idea to keep a schedule. I'm planning to. I'm not going to load them up in advance. I'm going to give them just about an hour or so ahead of each time because I like routine. It's been really quite lovely to be able to stick to a routine. Let me go over what it's about. At first, what the syllabus is. We're going to deal with some simple concepts of fossil soils, and I'll get to that later on in this lecture. But the first bit of the course is mainly about what a fossil soil is and how we can recognize a fossil soil. The problem with fossil soils is that they are in sedimentary rocks generally, or sometimes in volcanic rocks. So where does the sediment end and the soil begin? It's a problem. And it's a problem especially for people who are interested in and who have studied geology, because soils are generally studied in agricultural departments, not in geology departments. Although that's changing. We have two faculty here at the university who study soils. Matt and Josh both study soils, and they have active programs in soil formation. I'll talk about how you recognize them, about how we can infer processes from soils. But in the first part, I'm going to emphasize soil classification, particularly the classification of what used to be the U.S. Department of Agriculture, is now the Natural Resource Council. It's a U.S. soil taxonomy, which has a bunch of unfamiliar names: entasol, inceptasol, spodosol, oxisol. They all end in SOL, so that's nice. And they have a peculiar kind of way of constructing the names with modifiers. It takes a bit of getting used to, but it really is the lingua franca, the common language of soils, used throughout the world. And it's a very good way to think about ancient soils as well, because we have a diversity of soils now on the planet, scattered around in different places. What's interesting is seeing how those different kinds of soils and the ecosystems that created them have evolved through geological time, going way back to the very, very beginning. I'll talk about mapping and naming of soils and diagenesis of soils, because when the soils get buried, diagenesis, which is the process of alteration during burial, will change them. It's a little more confusing than that, actually, because diagenesis is not defined as just alteration during burial. It's defined as alteration after deposition. And so soil formation in a sedimentary basin is a form of early diagenesis. The sediment is sitting there, it's being altered, it's being weathered, it's being rooted, it's being burrowed, and that soil is therefore changing from the original sediment. And then it gets buried, of course, and then there's more alterations as it gets buried and compacted and maybe cemented or otherwise changed at depth. So early diagenesis and late diagenesis, these things blend into one another a little bit. It's a little tricky to tell them apart, but it can be done. There will be a test, a midterm test, on April 21st, and that midterm test will be multiple choice and short answer. The test will be remote. It'll be in that class period. I'll release the test to Canvas, and you will have, well, several hours to complete it, and email it back to me as either a Word document or a PDF, whatever you can manage. Certainly by the close of that day. It is, of course, going to be open book, and it should not be too difficult for you, I think. What is difficult, of course, is multiple choice. So don't get too panicky before the test. The thing about multiple choice is that they have tricky wording. They hinge on the wording of the question that predicates what the answer can be. So it's a good idea to get a good night's sleep and feel fresh when you go into a multiple choice test, so that you are on your game for picking logical construction of English grammar. That's what it hinges on in many multiple choice questions. For short answer questions, either illustrated or by a short text, it's a little bit more easy, and you'll have resources to answer those anyway. So that's the first part of the course. For the second part, I'm going to have a section on soil forming processes. By processes, I mean the factors that create a soil. So modern soils, we know, are created by 5 factors: climate, organisms, parent material, topographic situation, and time for formation. Why we go through this is because we want to have an understanding of how soil forms in order to understand how a fossil soil has formed. So fossil soils have climatic features that are useful for reconstructing paleoclimate. They have features of the organisms that lived in them that are useful for reconstructing ancient ecosystems. They have features that tell us about the kind of relief or relationship to water table in the past. They have features that tell us about the parent material, and those are generally the less altered materials, lower within the same altered profile. And then they have features which reflect the passage of time during which the soil formed, usually in a break between sedimentary deposition or maybe volcanic deposition of different lava flows or volcanic tuffs. So far in the course, 2/3 the way in, it's a course pretty similar to what you get in a course on modern soils, except I talk about diagenesis and burial, and I'm emphasizing features in paleosols that are likely to be preserved. Not all the features of modern soils are preserved. For example, pH and EH in the fossil soil are not the same as they were in the modern soil. We have to infer them from things that we can actually see. From then on, I'm going to go through the fossil record of soils, starting at the very beginning. Soils in space, one of my favorite lectures. We'll talk about soil formation, which is really weird on the moon and on Mars, and a little bit on Venus as well. Really weird kinds of soil formation that are unlike anything on Earth today, but are interesting because we know some of these paleosols on Mars are really old. And they look a lot like really ancient soils on Earth. Next, we'll move on to really ancient soils on Earth. We have them as old as 3.7 billion years in Greenland. Very interesting kinds of acid sulfate soils, which show crystals and other odd things that we find these days in only a few parts of the Earth, primarily in Paleolithic and desert environments. Soil formation in the very early Earth was quite different from what it was like later on. I'll talk about other Precambrian soils as well and how we seem to transition through into soils that become much more familiar and much more modern looking. I'll talk about life in soils and how we now have evidence that there was life in soils on Earth all the way back to 3.7 billion years. There are tantalizing hints that the 3.7 billion-year-old paleosol on Mars also supported life. But definitive evidence for that will have to await return of samples from everybody's favorite rover, Percy, currently active on Mars. I'll talk about soils of early land plants, and I'll talk about soils of early forests. We can tell quite a bit about the colonization of the land by land plants and by forests by looking at roots and other features of ancient soils. And then finally, I'll talk about grasslands and how grasslands changed our planet in so many interesting ways. Cooling the planet, for one thing, in which we find that there are lessons for farmers. I'm a part of a movement, Soil for Climate, and carbon farming movements, which are now starting to figure out how we can put carbon back in the soil where it belongs, and so mitigate global warming from atmospheric carbon dioxide by a series of effective agricultural practices. Since about 25% of the land area is managed in farms, we think that this is a very effective way to move forward from our current environmental crisis. The final exam, which will be on June 7th, 2 hours ostensibly, but you probably can take longer if you need, will have one component which is very similar to the midterm. It will have short answers and multiple choices of material that was covered since the midterm and not before. So that will be pretty routine, but there will be another component. I want you to write 2 essays. I want you to write 2 essays that are structured in a way that was not given in lecture. The short answer multiple choice just regurgitates information given in lecture and that you can look up in the book. The other part will be to put things together in a way that they were not presented. When I was a student, I was nerdy enough to really enjoy exam week because I was memorizing stuff and I was learning stuff and I was hitting the books and refreshing my memory of lectures and ideas. And all this stuff was swimming around in my head, and sometimes things came out with interesting connections that got me quite excited. A part of it was, of course, the vision of the lecturer, what the lecturer was trying to convey to me, but sometimes these were original thoughts as well. So I'm one of those odd people who really enjoyed exam week. But what I'm hoping is that with this structure of an essay, you will put things together in a way that were not quite the way they were presented to you, and it will lead you to independent thinking on this topic. Now, time is not going to be too short for you in doing the final exam, so don't sweat it. What you should do before you start the essay is outline. Make an outline of where it is going. What are the major things that you want to talk about in the order that you want to think about it. You can put this in a Word document, or you can handwrite it and scan it and send it to me. Either way, or you can just leave it off. But take a moment to reflect where the essay is going, because what I'm looking for is a well-crafted essay with good grammar and spelling that is persuasive, that is something that will convince me that you know what you're talking about. This is, of course, a skill that you're going to need in later life, in all walks of life, being able to write a persuasive document that persuades people that you know what you're talking about. The labs. We meet in lab personally, which will be awesome. I have a fantastic set of rocks and fossils. A lot of the lab will be sketching them or doing little exercises with them. I think you'll enjoy these materials. They're quite distinctive, and they're not like anything else that you've ever had in a geology course. The lab is starting at 11 a.m. in Columbia, room 47. You may need to get key access to Columbia Hall, and Marla is our departmental secretary. She has the office open Thursday mornings, I think, to 1. So you'll need to, or you can email her, that you will need to add a code, or someone will need to add a code to your student card so that you have access to Columbia Hall. Our building, this one, Cascade, where I'm giving this lecture, and Columbia, all our buildings are closed, but have card key access. If you want to contact me, you can email me, or you can give me a ring, and I can let you in from the top of the stair at the bell tower of Cascade. We can meet one-on-one if that's needed, and of course I'll see you every week, which is really quite a treat because our other classes are mainly remote. What we'll get out of the lab is there'll be one on root traces. You'll see some actual examples. Root traces don't look quite like you might think they would in all cases, so there's a variety of those. Soil structure, that's a really weird thing for a geologist to understand. Soils have structure, distinctive structures. They're not sedimentary structures, which you're very familiar with, I'm sure. They are soil structures. You need to know how to recognize them. There'll be a lab on petrography of soils, which is microscopic examination of soils. A lab on chemistry. That one is just a computer exercise using Excel. I can certainly help you with that if you need. There'll be some fossil soil horizon labs, picking out fossil soil horizons from suites of specimens and then field photos of the actual profile. There'll be a lab on diagenesis of fossil soils to familiarize yourself with what happens when soils get really buried and altered. Then there'll be a lab on wetland paleosoils of coal measures, and also on arid land soils of calcareous red beds. There's an optional lab on laterites and bauxites, which are also soil products. That's not a necessary one. However, I do want the 9 labs. I want you to hand in your sketches or text or both for all 9 labs, and they will be graded on the basis of participation, not on getting things right. It should be possible for you to put them in my box in Cascade Hall, or hand them to me during the lab session. It will be graded. Most of you will get 4.5 out of 5 for a lab, and that's a fair effort. If I think I want a bit more, I'll give you a 4. If it's truly outstanding, I'll give you a 5, but I won't keep doing that. The aim is to keep you all bunched up together on the lab scores. It's not meant to discriminate you. It's meant to, between you. It's not meant to sort you out. It's meant to um, keep you working, keep you at it. The labs will also, you'll do it in 1 week. I'll set you up on it. I'll be there to help you on it. And then the next week, before we start, I'll give you the answers in lab so you can self-correct your labs. Then you can hand them to me, and then I'll keep, after you've self-corrected, and then I'll try to return them to you the next week, because these labs will be very useful for your learning as we go forward. Sadly, I put in a possibility of an excursion here. Nope. COVID has intervened. The pandemic means there will be no excursion this year. I put it in there because, well, there seemed a chance, but there is not. The university will not allow excursion, transportation, and university vans for 4 hours out into Central Oregon, which is really one of the most wonderful places to see these things. However, if you wanted to go out there yourself and do an independent study of a paleosol, that would be fine. You need to go out in your own cell of people that you shared the pandemic with, or just individually. I went out there myself just last week. It's a beautiful area. The whole area is quite fantastic. There were 3 of us, and we all went independently in our vehicles and had masks on when we were in the field, where we had to discuss things. But if you went out there by yourself, you wouldn't need to take a mask or anything. The restaurants are open for indoor dining. Gas stations are all good. The roads are excellent. You can certainly do that if you wish to take an excursion. And who doesn't these days? So we've been indoors so long. It was really refreshing when I had the opportunity to get out last week. There is a term project, however, and the term project is important. There are 2 kinds of term project. Traditionally, the term project has been a description of a paleosol, which you studied in Central Oregon on the excursion. And since I never made the excursion compulsory, there were always a few people that did other things, some sort of essay on paleosols. And you can still do that, 15-page paper on, with including illustrations, written like a scientific paper about some topic in paleopedology or a particular paleosol that you might be interested to study. But increasingly in recent years, I've had an alternative project, and that project is to embellish a Wikipedia stub. I am a great fan of Wikipedia. It's in the pockets of 2.5 billion people, this English Wikipedia. Of course, it's in multiple languages as well. It's a unique resource. And I know many academics, when it first came out, poo-pooed it as being non-expert testimony, but it's getting better and better. And if it does have deficiencies, I think we academics should be ashamed that we did not fix them. It's our duty to edit Wikipedia. It's easy. Anyone can do it. You register for Wikipedia, and you can give your real name or an anonymous name, whatever, and then you edit away. I can give you some coaching if you need. Most people take to it pretty well. It's a little bit difficult to get used to the Wikipedia code. One way to do it is to register and then go to edit a page, and then just copy and paste it and see how it's done. See the different symbols and what they do. You can switch between edit mode and publish mode to see what the difference is, see how they cite things. One of the trickiest things is that any citation of a scientific paper has to be included at the point that it's cited, the whole citation, and it has to have separate fields for all the different items: the author, the year, the title, the journal, the volume, and the pages, and also some sort of DOI, some sort of document identification number as well. More and more students in my courses have been finding this a very rewarding option for a project, because it's something you can show family and friends, and you should be justly proud of a professional job. The project will require me, of course, to know what your project's going to be about first up, so I can make a copy of what's already there, so that I can see what you've added to make it more substantial, and whether it's a worthy addition. And of course, later on, your edition will be edited by somebody else and get better and better through time. There's lots of suggestions here in this. I've listed quite a few. A number of topics: paleopedological record, Precambrian paleosols, mollusol fossil, lunar paleosols, gelosol fossil record. These are quite needing in more information. As far as illustrations go, depending on what topic you choose, I can certainly upload illustrations to Wikimedia, which you can then call out in your article to embellish it. But mainly you're going to be doing what you would do for a term paper anyway, and that is going into the primary literature and creating a well-referenced summary of the topic at hand. The textbooks, well, you'll definitely need this. This is the lab guide, and all the labs in here have a pre-lab, a written account. You can get this at the university bookstore, not too pricey. They have a pre-lab, and then they also have an exercise, which is what you will fill out and do on your own sheets of paper, and then hand in to me the next time. The textbooks are by me. This is it. This is my pride and joy. Woo, where are we? 2019. I'm not sure you'll need the text. You're welcome to buy it. I think you'll find it helpful. The lectures do follow the text pretty religiously. That's because that was the way I set it up. There are secondhand copies, not of that one. That's a 2019 edition. There'll be a few on sale at the bookstore. This is the 1990 version, if you can find one of those. That will do nicely. This is the 2001 version. That also will do nicely. Another one that you might enjoy is this one, A Color Guide to Paleosols. This is actually a very expensive option. This was a book that was designed for geological professionals who want to get a crash course in paleopedology without taking an actual course in it and without laboring over it too hard. It has lots of lovely pictures in it, including color pictures, including a lot of the materials that you'll see in lab. This now sells for hundreds of dollars, sadly. If you see one secondhand or on eBay or something, probably worth snatching up if you're interested, but not essential. I think you'll get by pretty much with the materials as I present them in lecture. I hope we're good with all that. I have a little bit of time left here, and I want to get through some really basic things about paleopedology. So, paleopedology. It's the study of ancient soils. It has nothing to do with child psychology, so nothing to do with pediatricians. That one comes from a Greek word, pais, paidos, which was child. Nope, not that one. It doesn't have anything to do with mummies' feet either. That one, for pediatricians, for example, that one is from the Latin pes, pedis, which means foot. No, not that one either. It actually comes from a Greek word, pedon, pedu, which means soil. So pedology is the study of soil. And paleopedology, we just tack a paleo on it, and that means ancient soil. The idea then is that these are soils of the past that are either dead and buried in the fossil record, or that have persisted at the surface even though everything has changed. They represent a surface that is indicative of soil-forming conditions of the past. Now, the main problem for paleopedology is not really these definitions. Nobody's going to confuse it with children or feet. It's that there's a variety of definitions of soil itself. So what exactly is a soil? Well, to a farmer, a soil is the fertile upper material in which you grow a crop. To an engineer, a soil is anything that does not require blasting to move, that you could just move with a standard D9 grader. You can just push it aside with heavy equipment. To a geologist, we have the idea of a soil profile or a weathering profile that extends at depth. It's a soil profile that goes down from friable material at the top all the way down into hard material at the base. Think, for example, of a soil developed on granite. Eventually, you're going to get down to that granite. And so from a geological perspective, the whole thing is a soil until you get to the stuff that rings to the crack of a hammer in the hard crystalline granite at depth within the profile. Now, this is a problem, especially when we start to deal with soils on the Moon, on Mars, and in the Precambrian. If you take the farming view that soils are a medium for life, and that's what defines them, then we don't really know whether they have life on those other planets or in the Precambrian. May not have had life on land. Why would you wrap a definition of something up into the major question? There's $2.5 billion missions, two of them now, Curiosity and Percy, to Mars, trying to answer that question. Why would you wrap that up in a definition? That's the major question. Is there life on Mars? That's what we're trying to answer. But we certainly can recognize that in a Martian sequence of sedimentary rocks, there are horizons that look like paleosols. The question is, did that paleosol support life, or was it barren of life? Did it form just by chemical processes and physical processes, or was biology involved? That's the question we want to answer. We don't need to wrap that up into definitions. So I take a broad brush that soils include things that are formed by biological, by chemical, and by physical processes on a planetary body. All three can form a soil. And the job of paleopedologist, of course, is to disentangle which of those three are most significant in their formation. Now, mostly we'll be dealing with soils that are in sedimentary environments, or in volcaniclastic environments, volcanosedimentary environments. Let's imagine we now have a place like the Willamette Valley, in which there is a soil formed on bedrock, late Eocene sandstones of the Eugene Formation, in a valley. The floods deliver material. That material has ripple marks and other sedimentary structures in it. And then after the flood, the grasses grow and start to put roots down into that material and develop a soil. The cows graze over it. That soil then is developing. Let's say there's another big flood, a really nice big one, and the grass starts to grow, and then eventually it grows up until it becomes a forest. And with a grassland soil, we just generally have an A horizon over a C horizon. That's organic plus mineral. This is just weathered material. If we go all the way to a forest, we start to get a horizon which is rich in clay. Now, this kind of a soil, just a grassland soil with an A horizon over a C horizon, may take something like 100, 200 years to form. This kind of soil will take several thousand years to form. The tree roots channel down into the underlying material so that clay is alluviated into a horizon, which is called a BT horizon. Here's the A horizon. That's organic plus mineral. Here's the B horizon, which is clay enriched. The sediment with ripple marks and bedding overlay this altered material. And then the whole thing was altered over a period of several thousand years to have a rather rich soil, which is very strongly altered from the original silt and sand of the original flooding event. This is now a relatively well-developed soil under an oak forest. Now let's imagine there is another flood, not so thick this time. And that particular one develops a BT horizon, which now overlaps the A horizon of the underlying soil. So this is A, BT now. What we have here in this horizon is what's called pedorelics. That means within this later soil, we have some features which are due to the A horizon, which are overprinted by features from the BT horizon. We also have, in these cases, sedimentary relics. Which are structures that remain to illustrate the flood that buried the profile. These sedimentary relic structures are important as evidence for the mechanism of the deposition of the parent material. And then finally, we can erode out bits and pieces of this and redeposit it in other places where it's all soil material and it's quite different from the sedimentary material. This is called a pedolith. A pedolith is a redeposited soil unit, maybe redeposited by landsliding or maybe redeposited by a flood, that has a soil composition but a sedimentary structure. These are interesting alternatives, and this is why sometimes in teasing apart these different alternatives, the original soil features, the sedimentary features, and the relic features, why sometimes it's difficult to recognize within any given stratigraphic succession a individual paleosol. What we need to look for especially are ones like this, which have the sedimentary material here and here, with a clearly truncated upper surface and then good soil structure going down gradationally in a horizon into the underlying material. Those are easy to recognize, and if we can recognize those, we have a good idea about what one soil looks like. In situations where they're jumbled up together a little bit, it's a little harder. So in mapping out paleosols, you need to be aware of these different complications that we can then disentangle the the different features of a profile. By going for the ones that are obvious to start with, we can then start to disentangle the ones that are overlapping. Now, there are lots of really lovely places where you can see these sorts of processes in all their glory. And I particularly recommend the Painted Hills of Central Oregon. If you want a road trip, which is deeply satisfying, do consider the Painted Hills. This is where the geological excursion for this course has traditionally gone. And there you can see these red paleosols, one after another, beautifully exposed in the Badlands. The Painted Hills is one unit of the John Day Fossil Beds National Monument. The other unit, the Clano unit, with its lahars and paleosols, and then also the unit near Dayville there that is near Sheep Rock. Those are just beautiful places to see paleosols in action, and also the Sheep Rock Condon Paleontology Center has wonderful displays of the fossils that are found in these paleosols. This is what got me into paleosols in the first place. Paleosols commonly have the fossils of the creatures that lived on them. Fossil mammals in the case of Central Oregon, and also some fossil plants. But I got my start looking at fossil soils of this sort here in sedimentary sequences in the beaches of Sydney back in the day when I was a blonde-headed stompy-wompy real-going surfer boy, and started to look at the sea cliffs for fossil plants. And I found that many of the soils, the fossil soils in those units of Triassic age, had beautifully preserved fossil plants in leaf litters around them. So that's a kind of a brief sketch of what paleosols are and how they form some of the processes. Let me just finish up by talking about the uses of paleopedology. Why would we bother studying fossil soils? Well, there are several. One is as a stratigraphic marker. Each paleosol is an ancient land surface, and that land surface is sort of more or less the same age across the landscape. And they can be separated by different packets of sediment, of course, by different flooding, landslide, and other episodes, even erosional episodes. But sometimes we can trace them across the landscape so that we can use them to divide up sedimentary units. This kind of use has been especially important in looking at glacial deposits. Because frankly, if you've seen one loess deposit, loess is spelled this way, German, you know, one windblown silt deposit looks like another, but paleosols often have a lot of character to them. They often have very distinctive, colorful horizons and horizon sequences that are better recognized laterally. So paleosols have commonly been used to divide up loess and till deposits, particularly in the Midwestern part of the United States, but also in other areas of the world. There are limitations to that, and we'll get to them as we go on further. I think the best use of paleosols, the most interesting one, is for reconstructing paleoenvironments, ancient environments. And this has been the course of my own academic study for many years. The sort of soil that forms under an oak forest is red and clay and thick, the sort of soil that forms under a grassland is thin and brown and granular structured. Very, very distinctive. And just from the soil itself, you can tell whether it was a grassland or an oak forest. That's kind of remarkable. That's actually very hard to do even if you have fossil plants, because the plants are not normally preserved in the place where they grew. And the soil is forming in the place where they grew. It turns out that information on ancient environments um, for paleontologists and for many others, including paleoclimates, is very usefully gained from the study of paleosols. One of the things that's emerged from studying paleosols of all ages, and I've really enjoyed this myself, is the history of pedogenesis. Pedogenesis is just the study of how soils form, genesis of pedons, soils. It turns out that through the great sweep of geological time, especially with the change of biological agents of soil formation, like grasslands only go back to the Miocene, forests only go back to the Devonian. Before that, there were vascular plants going back to the Cambrian, maybe. Before that, it was just microbes. As the life on Earth has changed, so have the soils. So we're starting to get a kind of a very interesting historical perspective on how soils have changed through geological time, and how that's related to the environmental changes that we see in Earth history as well. There are also economic geologies implications. Some paleosols are mineable, in particular laterites, bauxites, and silcrete. Laterite is a source of iron ore. It was enriched by soil-forming processes in tropical soils generally. Bauxite is a source of aluminum ore, again enriched in deep tropical soil. Silcrete is often used as a refractory material in foundries, and it also formed by soil-forming cementation processes. You don't have to be too much of a paleopedologist to find these ores, but having knowledge of paleopedology does help you in understanding where and how they formed, and the quality of the ore for the particular purpose that you might have been hired. So some economic geologists are, in fact, paleopedologists. And then finally, there's just curiosity. And in fact, that's the main use of paleopedology these days. It's part of the curiosity industry. There is an industry of curiosity. That industry is jobs in universities like this one, and also in museums. You can get jobs in paleopedology working for museums and working in universities. There's about a dozen paleopedologists around. It's a small field, but one that's growing ever more popular. And it turns out to be an important aspect of historical geology, which has been neglected for many, many years, and which is just now coming into its own, revealing big changes in Earth history and in the kinds of soils and how that relates to paleoclimate in deep time. These sorts of uses are what keeps many of us going. It's a great field if you're interested in landscapes, in life, in climate, and getting a broad perspective on the history of not only our planet, but also other planets. We have discovered paleosols on Mars, and we do hope that Percy, the latest addition to our fleet of Mini Cooper-sized rovers on Mars, will find more. And we are expecting surprises. So that'll do for today. I'll post another lecture on Wednesday, and I look forward to meeting you all in Columbia 47 on Friday. Thanks for your attention.